go home to be there when the swimmers come this morning, so, or this afternoon, so that's why tomorrow. Okay, so last time we kind of left off our discussion of preparation of tertiary alcohols. And so if you had a tertiary alcohol like this, there were three ways to make it, either by disconnecting this bond, in other words, thinking of ethyl adding to the carbonyl, so you make this bond last, or disconnecting that bond, in which case methyl adds to a different ketone and so on. And so whenever you see a tertiary alcohol or secondary alcohol, you have to be able to discern various ways in which that compound can be prepared from carbonyl compounds. Okay? Now, then that was the next to last thing we talked about. The last thing we talked about was formation of acetal. And we said that this is really no different than the formation of a hydrate. It's essentially the same mechanism. The difference being that one can drive the equilibrium towards acetal formation, and that acetals don't have that hydroxy group. As it turns out, they're going to be useful as protecting groups, and we're going to see an example of that. One particularly useful acetal is the one that you make from ethylene glycol. And this is the cyclic one. This one turns out to be quite a bit more stable than ones like this. And so these are chemically robust and are used quite often as protecting groups. Now, the mechanism, which I also went through, I'd like to go through in some detail because it is the same mechanism that you're going to see again and again. Okay, so this mechanism is sort of an archetypical kind of so let's just take a ketone, and another ketone, and methanol. And so remember that these reactions take place in acid, and so you end up forming reversibly a conjugate acid of your carbonyl, like so. And this conjugate acid is depicted by two resonance structures. Okay, so I can show two resonance structures for this. Now, why do you do that? Well, because you'll notice that although this carbonyl carbon has a partial positive charge and therefore will react with nucleophiles, this is going to be far more reactive because this bears a full positive charge. Okay? And so methanol can act as a nucleophile and can add to the carbonyl. Now, if that happens, this is another equilibrium. If that happens, then what you end up with is the part of the molecule that didn't change. Okay, that's this part. And then this is the bond that I just made to methanol. Okay? Now, this has, of course, a conjugate acid, and in the presence of methanol, I don't have to tell you that that proton is exchanging rapidly, right? So it goes on, it comes off, goes on, comes off. So at some point, I'm not going to show each and every proton transfer here. So imagine that methanol comes along and removes that proton. Okay, so now you have a different compound. You have this one, which is in fact, because you have a hydroxy and a methoxy, this is what's known as a hemi-acetal. Okay? Now, for the acetal, remember that I want this to become a methoxy group. Now, how is that going to happen? Well, methanol has to somehow attach itself to that carbon atom. Now, how did methanol attach itself to a carbon atom here? Well, I had a positive charge on that carbon atom, right? And so how do you suppose I'm going to get a positive charge on this carbon? Well, it's a reaction we've seen before. You do a proton transfer to the hydroxy group, and then you get a kind of an SN1 process. So if you have protonated methanol or whatever else, proton transfer can take place reversibly from this lone pair to there. This is another reversible reaction. Now you have
which can do the normal thing that we've seen before. It can give you water, and in a kind of an SN1 process, it can give you this cation. Now, is this a good cation or not? Well, it's tertiary, plus it is oxygen stabilized. I can write a resonance structure for this that I'm not going to bother to do for you. And so this cation, just like this one, can now be intercepted by methanol. So methanol comes in and traps that cation. This is, once again, a reversible process. And there's the conjugate acid of what we want. So loss of a proton from this gives the acetal. So the things to notice are that this is acid catalyzed, and the mistake you don't want to make is to show an SN1 type reaction where hydroxide is the leaving group, right? So that tells you that you need to get this proton transfer here before you're going to break that bond. So you're not going to be able to do that here. So in other words, neither hydroxide, OH minus, nor methoxide, OCH3 minus, is going to leave that carbon atom. Because why? Because OH minus is a strong base and it's not a leaving group. H2O is not a strong base and therefore is a leaving group. We went through all of this in Chem 272, now it's coming back, you see. So this mechanism is pretty much the same for all of the nucleophilic additions that we're going to see in this chapter of carbonyls. So please make sure that you can reproduce this mechanism on your own. It's not, you'll see enough of this now that I think it should become second nature to you. Now, there's something else that you need to be aware of. And something else is this, that you can go from the ketone or the aldehyde to the hemiacetal. Remember, hemiacetal had an OH and an OR. You can do this with acid or by base. So this first step can be base catalyzed, but the second step, where you go from the hemiacetal to the acetal, is only acid catalyzed. Okay, now I'm not going to go through why that is. You need to, I've told you actually why that is just a few moments ago. So convince yourselves that this is the case. If you try to go from here to there in the presence of base, then it's not going to work because why? Because you're not going to have a leaving group. That's why. Okay, so take a look at this reaction. Make sure you understand the mechanism, and then move on from there. Now, hemiacetals are rarely stable with ketones, but they're very stable with aldehydes often. And so aldehydes, and I shouldn't say never, I mean very rarely ketones form stable hemiacetals. So if I take acetylide methanol, equilibrium overwhelmingly favors the hemiacetal. And here's no acid, nothing. The trace amount of acid on the glass of the flask can catalyze that. 5 and 6 member ring hemiacetals, so cyclic hemiacetals, this is a cyclic hemiacetal, will form spontaneously. So if I look at this, look, I have a 1, 2, 3, 4, 5, 6 member ring. And so this is a hemiacetal, and what I want you to be able to recognize is that this carbon atom where I'm pointing to is the equivalent of an aldehyde. Okay? So when you see a carbon that's bonded to 2 oxygens or 2 nitrogens and a hydrogen, that's going to be, you should think aldehyde. If you see a carbon atom bonded to 2 oxygens or 2 nitrogens, bonded to a carbon and a carbon, then you should think ketone. Okay? And that's pretty much what you saw over here, right? I mean, this is a carbon atom that's bonded to 2 methoxy groups and 2 R groups. That's a ketone, equivalent of a ketone. And so going back and forth, here's another case of that, right? Here's a carbon atom bonded to 2 oxygens, 2 R groups, equivalent to a ketone. And when you go to the hemiacetal, it's really no different, just you have a ring. Now, this becomes very important in biology, right? Because glucose, the structure of which I've shown, is a stable hemiacetal. And so this carbon atom is unique in glucose. Convince yourselves. This is the only one that is bonded to 2 oxygens. The others, all the other carbon atoms are bonded to at most one oxygen. And so this carbon atom is the equivalent of what? Two oxygens and a hydrogen. It's the equivalent of an aldehyde. And so this equilibrium overwhelmingly favors the cyclic NES-tal form of D-glucose. It's the same with 5-member ring sugars too. And so these are the ones that form the backbone of DNA and RNA. But glucose is a stable hemiacetal, and so the carbon atom, this one here, which is called the anomeric carbon, we'll learn that sometime later when you study biology, this carbon atom, that one, reacts the way aldehydes do. And so it has the reactivity of an aldehyde. Okay, now, this discussion of hemiacetals and acetals and what have you brings us rather naturally to a discussion of protecting groups. And so the question you might have is, how do I do this? Why can't I do this? Okay, so look, I have this bromide, and I want to make that Grignard reagent, the red one that I've shown. That I will propose to you, that doesn't happen. You can't do that. Why is that? I mean, that won't work. You go to the lab and try to do that. Why? Well, what do we know about Grignard reagents? Remember what we said last time about Grignard reagents? We said that, you start with an alkyl bromide, you treat it with magnesium, you end up getting, from the bromide with magnesium metal, you end up getting the bromomagnesium reagent. But you think of this as being RCH2 minus magnesium Br plus. And so this is the reactivity of the Grignard reagent. So you always think of the Grignard reagent as being equivalent in reactivity to this carbanion. So why is it that that carbanion is not going to be compatible with this structure? It'll self-destruct, right? Because it'll react with that carbonyl. And so Grignards react with carbonyl. Remember what we talked about just moments ago? I said that if you have a Grignard and a carbonyl, you'll form the tertiary alcohol and so on. Well, if you try to make this Grignard, it's going to react not with this carbonyl in the same molecule, but with the carbonyl of starting material. And then if you are able to form the next Grignard, that will react with something else and so on. So that's never going to work. On the other hand, you really want the reactivity at this carbon atom to be nucleophilic. So I want to take this alkyl bromide, which is an electrophile, right? So I can do SN2 chemistry there, and I want to change it to this Grignard, which is a nucleophile of that carbon. How do I do it? Well, I can't do it in the presence of the alcohol. No way. So that means that alcohol, or this ketone, I can't do it in the presence of that ketone. That ketone has to be protected. And so the way you do it is you take ethylene glycol and acid with water removal, and you form the cyclic acetal. At this point, I no longer have a ketone, so there's no reactivity at this site to the Grignard. That allows me to make the Grignard just fine. Now, I can do whatever I want with this Grignard, and then in another step, I can reverse the formation of this acetal, because why? Because I can use the Chataigne's principle, treat that acetal with excess water and acid, and then push the equilibrium back to ketone. And so this is how a protecting group works. You end up temporarily masking the reactivity of a functional group. So you can think of it as some kind of masking tape. You just put masking tape on that functional group, nothing happens to it, then when you're done, you rip the tape off. And so that's how protecting groups work. Now this is a protecting group that works for ketones or aldehydes. There are many, many other protecting groups for diverse functional groups, alcohols, esters, and so on, and amines. So, but the key to all of these protecting groups is they have to be introduced and cleaved with high efficiency. In other words, if I have a protecting group and I can only get a 50% yield of putting it on and a 50% yield of taking it off, then all of a sudden I'm left with 5 times 5, I'm left with 25% of the material I started with. I lose 75% of everything. that clearly is not going to be practical, right? So if a protecting group is going to be useful, it's better the yields of introduction cleavage have to be very high. Now, one thing that you probably would not think of is that in large molecules we have multiple protecting groups, right? More than one. Now, if I want to remove, say, 3 protecting groups, identical ones for a molecule, then this business of high yield becomes much more important, because if each one is cleaved with 99% efficiency, I end up with something like 98% overall efficiency, 97%. If each one of those is cleaved with 80% efficiency, then I lose a huge amount of material, because the overall yield is 0.8 to the 3rd power, right? And so at that point, my overall yield is less than 50%. And so the efficiency of protecting group removal is going to be even more important. Okay, now we saw that aldehydes and ketones react with water to form hydrates. We saw that aldehydes and ketones react with alcohols to form either hemiacetals or acetals. And so the question comes up, well, do they react with amines? And the answer is yes, they do. And with primary amines, or ammonia derivatives, to see what we mean by that, you end up getting these carbon-nitrogen double bond compounds that are known as either imines or Schiff's bases, named after the German chemist who first described these in the 19th century. And so you have a heteroatom, in this case not oxygen but nitrogen, with a lone pair, so this is nucleophilic. You have an electrophilic carbon atom, and then something happens. Okay, so what happens? Well, you saw the mechanism that I wrote for the formation of an acetal. And so the mechanism here is really almost the same. So if you know the mechanism for the formation of the acetal, then you can kind of understand what the mechanism is going to look like here. The first step is the activation of the carbonyl by acid. Okay, so the carbonyl reversibly gets protonated. The protonated carbonyl, that's that one right there, is more reactive towards nucleophiles, because now, in one of the resonance structures, that carbon atom bears a full positive charge, not a partial positive charge. And so the amine can attack that carbon atom to form this tetrahedral intermediate. Same step that we saw with the hemiacetal or acetal. This can lose a proton reversibly, and this can add a proton reversibly. So I'm not going to show each proton transfer. At this point, you have a leaving group. This electron pair then can come in and kind of, you can think of this as pushing out that leaving group, and it will give you this protonated form of the imine, and then loss of a proton just gives you the imine. And so the reason that you don't get 2 nitrogen atoms there is because why? It's because the nitrogen because nitrogen can form 3 bonds and oxygen can only form 2. And so here you end up forming a slightly different type of product with only 1 nitrogen attached to the carbonyl. Now, when you see an imine, however, I want you to see the equivalent of either an aldehyde or a ketone. In this case, it's an aldehyde, because that's a hydrogen. And it's really no different from what I said before. You have a carbon atom, it's bonded to an R group and a hydrogen, and it's bonded, in this case, you can think of it as being bonded to 2 nitrogens. Well, not exactly, but it's doubly bonded to 1 nitrogen. Same thing, right? So that's a carbonyl equivalent. Now, the rate limiting step is usually this one. This is what usually takes the slow step. Now, there's a slight difference in the formation of imines over acetals that we saw, and that is that you have to be careful when you set up an imine formation. You have to be careful not to use too much acid. You can say, well, but acid is a catalyst. How can I have too much? Here's how. Remember that this is fairly basic, and so if I have an excess of acid, I'm going to completely convert my nucleophile into this ammonium salt. The ammonium salt is no longer nucleophilic because it doesn't have a lone pair. And so with more than one equivalent of an acid, or even one equivalent of a strong acid, this reaction is not going to take place. Because why? Because your nucleophile has been converted into an ammonium salt. It's no longer nucleophilic. And so excess acid, no good. Okay, so imines are important for a number of reasons. There's an important reaction in biology called an enzyme called aldolase. And one of the steps involve enamine. We're going to see an enamine catalysis. And this aldolase mechanism has been an inspiration for development of a whole series of important catalysts. But, and we'll see enamines in a minute. But in the meantime, let's take a look at, these other ammonia derivatives. Okay, so you can think of this as being an ammonia derivative, right? If you have NH2 with this whole big piece attached to it. Or here you have NH2 with a hydroxy attached to it. Or here you have NH2 with this urea piece attached to it. So this is called hydroxylamine, this is called semicarbazide, don't worry about that. This is 2,4-dinitrophenol hydrazine, 2,4-dinitrophenol, and then NH2 is hydrazine. Now, these derivatives, okay, so these all react with ketones or aldehydes to give either this kind of an imine or this kind of an imine. These have different names, or this kind of a derivative. These derivatives typically are highly crystalline. And years ago, before people had spectroscopic tools, the melting points of these derivatives were used to characterize compounds. And so how did that work? Well, people would report the melting points of say, a ketone's 2,4-DNP derivative, oxime, and semicarbazide. These melting points are sharp, and they differ by a lot depending on the structure of the ketones. If you have an unknown ketone, you form one of these derivatives, purify it, take the melting point, look at the table of melting points, you can nail the structure. And so occasionally that's still an important thing to do, believe it or not. And so these still have some currency, but clearly not nearly as useful as they were before the development of IR and NMR. The mechanisms for formation are pretty much the same ones that I showed you for the imine. Okay, so take up, you can figure out how that works. Here, notice that dilute hydroxide can work too, and your book explains why that is. Okay, now let's take a look at what happens when you allow a carbonyl compound to react not with a primary amine. Primary amine, remember, has two hydrogens on the nitrogen, but with a secondary amine, like morpholine. And in this case, you don't form a carbon-nitrogen double bond species as your product, form a carbon-carbon double bond species. And so if I allow cyclohexanone to react with morpholine in the presence of acid, I end up with this thing that's called an enamine. Now, why enamine? Well, because it's an an alkene, and it's an amine. Okay? And I get water. So in order to get this reaction to go from left to right, water has to be removed from the equilibrium. So it's an equilibrium process. I haven't shown it here, but it is an equilibrium process, and water has to be removed, otherwise you end up with a mix. The mechanism is no different from the mechanism for formation of an acetal, really no different than the mechanism for the formation of an imine. It's all the same, nothing different. So the first step, always the same, activation of the carbonyl. The second step, nucleophilic addition, proton transfers to convert this hydroxy into water. And then, the same kind of thing, you get an SN1 type process. I've shown this resonance structure. I could have shown the other one as well. Now, this cannot lose a proton. Notice that there's no proton to lose. Notice that when we talked about imine formation, after loss of water, there's a proton here. So loss of this proton led to the imine. That proton is not present because, guess what? I started with a secondary amine, not a primary one. And so the proton that gets lost is not the one on the nitrogen, but the one on carbon. And so that's the only difference in the mechanism. And so you can say, well, that's a trivial difference because, you know, it's kind of self-evident that there's no proton to lose here, so you're going to have to lose a proton somewhere. And so once you lose that proton, you end up with the enamine and H3O plus. So you can see that it's essentially the same mechanism. Now let me ask you a trick question. Just draw this structure again. Okay, so we have this structure here. Okay, that's the structure. And we said that we lose a proton from that carbon atom, or that one, right? I mean, these two are identical, so that's not a problem. Why is it that I can't lose a proton from here? I mean, why couldn't I just as positively charged nitrogen here? How come I don't lose that proton? Oh boy. We have an exam coming up. Actually, a week from today. We don't know. Well, let's try it. I mean, you know, I asked the question, let's try it. So, here's water. Pulls that proton off, and I go like that. Why is that not good? Ah, yes, an octet rule violation. This one person. Oh, there was a trick question. How come you didn't think octet rule? Because I have many tricks that I can play. Okay, so that's. Okay, so now there's a question, right? The question is this: how come? So what have we seen? We've seen that primary amines lead to imines. Secondary amines lead to enamines. Well, okay, so secondary amines can't give amines because why? Because there's no NH to be lost. Okay, but that doesn't answer the question of why primary amines also don't form enamines. They could have formed an imine or an enamine. In other words, there's nothing to stop this compound here. Well, this one doesn't has a. I picked a bad example to show you, but if this were cyclohexyl, then I could have lost a proton here if I had one too, and that would have worked to give me an enamine. So why is it that you get imines in one case, enamines in the other? And the answer is that imines are more stable than enamines, and so the C double bond N, sort of like a ketone, is more stable than the enol. Ketone more stable than enol, imine more stable than enamine. And so that's why the imine is preferred, except when you can't form it like with a secondary amine. Okay, so in terms, by the way, tertiary amines, it goes, you know, I probably don't need to even say that. Tertiary amines don't form stable intermediates, right? Because there's no way to form any kind of bond. There's no way to get rid of the charge, at least that's what it means. So tertiary means that, you know, they don't form stable intermediates. Now, all of these mechanisms, enamine, miniamine, mini-acetal, they're all the same. And so that's why I want you to do the hemiacetal mechanism, which is the first one. Make sure you understand acetal. Make sure you understand that before you go reading about enamines and the rest, because you're not going to understand the later stuff if you don't understand the earlier stuff. Now, we've talked about reductions of ketones and aldehydes, right? And we've talked about reductions using sodium borohydride or lithium aluminum hydride to form alcohols. But those are not the only ways to reduce ketones and aldehydes. And so you can reduce them all the way down to hydrocarbons, as shown here. So I can take a ketone or an aldehyde, and this little bracketed H just means reduction of some sort. And where the carbonyl was, you see it's been obliterated, and I have just two hydrogens. This is known as the Wolff-Kishner reduction, and it's illustrated for this aldehyde. The reducing agent is hydrazine. Hydrazine, by the way, is rocket fuel. Actually, dimethylhydrazine is liquid rocket fuel. And that has two methyl groups on one nitrogen. This is a very powerful reducing agent, and the conditions are are fairly severe. You take this with this high boiling solvent, which is called triethylene glycol. Why triethylene glycol? Well, because it's a trimer. It's 3 times ethylene glycol, right? You have these 2 alcohols condensed. Here's an ether. Condensed is another ether with hydroxy groups at the end. So you can think of 3 units of ethylene glycol in here. You take this thing up with potassium hydroxide and then heat holy hell out of it, up to maybe 180, 200 degrees. And what comes out is actually a very nice yield. Yields are usually very good of the completely reduced product. And so this is a useful reaction. The mechanism is a bit strange. I'm going to show the mechanism that's in the book. This may be a little bit not quite exactly right, but you form a hydrosome first, okay? So a hydrosome can be formed with base. You don't need acid to form this hydrosome in strong base. And the hydrosome then gets deprotonated irreversibly. And you end up forming this resonance stabilized anion. And at some point, water, which is the strongest acid there, you don't have any acid, right? This is done in potassium hydroxide. So the strongest acid there, water, protonates this to give you this compound known as an azine. Now this is unstable. And what this will do is it will spit out N2 and either give you an anion or a radical that gets reduced. And so the mechanism up to here is the same as we saw for the iminium ion, or the imine. Then it's just a proton transfer, another proton transfer, and then from here, this thing just collapses to give you nitrogen gas and the reduced compound. So it's a bit of a strange reaction for us. We haven't seen anything quite like this. How this thing collapses, there are 2 ways it can go. It can either go via a ionic mechanism, which will give you a carbanion here, or it can go through a radical mechanism, which will give you a radical there. I'll let you figure out those 2. It's not hard to do. Well, it turns out that there are many ways, of course, to reduce things, and the impetus for developing multiple methods to do the same kind of functional group transformation is that there are a lot of times when you have a multifunctional molecule that's like a stand-up to being boiled in lye, in hydroxide. And so there's an acid mediated reduction of ketones, again, all the way down to the methylene, using acid and zinc, usually with a catalytic amount of mercury 2. Now, the mercury 2 does the same thing here that I said that it can do for a Grignard reaction. That the mercury gets reduced to mercury metal by the zinc. That mercury metal amalgamates the surface of the zinc. It just forms like a solution of zinc and mercury. That changes the structure of the surface of the zinc and makes it much more reactive, and then the acid catalyzed reaction can take place to give you the product. The mechanism of this is fairly complicated. We don't need to talk about it. So Clemmensen reduction and Wolff-Kishner reduction are 2 common methods for taking carbonyls all the way down to methylines. There are many others too, by the way, and we don't need to talk about those. What I'd like to talk about next, though, is kind of an important reaction. It's called the Wittig alkene synthesis. Wittig was German, so it's not Wittig, it's Wittig. And if I take this tertiary alcohol and I treat it with acid, then I kind of reminded you of what happens. You get proton transfer, you get the OH2 plus, that ionizes, and it gives you a tertiary cation. And that tertiary cation can then lose a proton in one of 2 ways. You either lose a proton from here to give you the trisubstituted alkene, or it could have possibly lost a proton from there to give you the exocyclic methylene, but actually Markovnikov's rule tells you that you're going to get, you end up getting this compound. So then the question is, how to make a compound like this? I mean, how would one make a hexacyclic methylene compound? Of course, you can think of probably more than one way, but a very common and very practical way is in the following, as follows. You take cyclohexanone, and then you take a reagent that looks like this. This is a big molecule, right? Because it has 3 phenyl groups, positively charged phosphorus, and a negatively charged carbon atom. Now, these two atoms, positive and negative atom, are adjacent to each other. And whenever you have a dipolar molecule like that, that's called an ylid. And so sometimes you see this with an E, sometimes not. This is called methylene, and then triphenyl phosphorane. So phosphorylate. This reaction is done in the absence of water and air, and you end up generating very cleanly the methylene compound and tetramethyl oxide. Now, the driving force of this reaction is actually the formation of phosphorus-oxygen bond, because that's one of the strongest bonds around. It's better than 110 kcal per mole. And so that provides the thermodynamic driving force. This reaction goes all the way. I mean, it's not equilibrium. It goes, you know. Now, that's the good part. The bad part is that triphenylphosphine is expensive. And you'll notice that the mass of this reagent and the mass of this stuff is much greater than the mass of your product. So if you're making a kilogram of this, you're making roughly 3.5 gigs of this. And so if you're interested in doing this commercially, you've got one heck of a waste stream product. Not only that, but this isn't really waste. This is valuable and has to be recycled. And because this is a strong bond, you already know that reducing this back to triphenylphosphine is going to be kind of a trick. So there are some problems with it. Nonetheless, this is used on ton scale, believe it or not. So triphenylphosphine is a nucleophile, can react with dihydromethane, give this compound here, which is this crystalline salt. You can buy this, air stable, no problem. Once you deprotonate that methyl group with butyllithium, you need a strong base to give you the ylid. This stuff is very sensitive to water because the strong base that reacts with water, but also air, so it can be oxidized. And so the next reaction has to be done at low temperature and typically in the absence of air and water. So you can think of this acting as a nucleophile, just the same way that a Grignard is a nucleophile towards the carbonyl. Now the oxygen and the phosphorus can hold hands. And you say, but that's an octet rule violation on phosphorus. But remember that phosphorus isn't in the same row as carbon, and so no octet rule violation. And then this collapses, sort of the way we saw the collapse of the 4-membered rings in the metathesis reaction, to give you on the one hand the phosphine oxide, and on the other hand the alkene. These oxophosphatanes, by the way, are stable enough at about minus 100 degrees C that you can take an NMR spectra of them. So the way you know that you're getting this is you can follow the reaction by NMR. You do a low temperature NMR experiment, then run the NMR and let the temperature come up gradually, and at some point you start to see this plus that, and then you can follow the reaction by NMR. So that's one way to determine mechanisms. Now, in spite of all the problems that I indicated, that phosphorus is not cheap and that the phosphine oxide has to be recycled, this is still one of the best ways to make alkenes. Believe it or not, it's used for making vitamin A and astaxanthin. I'll talk a little bit about astaxanthin. So vitamin A is this stuff here, which is a terpene, by the way. You can see the terpene rule. Astaxanthin is also a terpene. And astaxanthin is a dimer. It's 2 of these joined right there. Astaxanthin is what? Does anybody know, I mean, if you go to a health food store, they'll sell you astaxanthin. And it's made from really slimy algae that they grow on the Big Island. And it's supposed to be good for you as an antioxidant. It's also responsible for the red color of cooked lobsters, as I recall, and that's where that asta comes from. That is part of the word for lobster in Greek. And so astaxanthin is formed by a Wittig reaction. You don't, okay, so two ways of making it. You can either make it from algae, or you can do it by chemical synthesis. Guess which way is cheaper, chemical synthesis. And so there's a company in Switzerland that kind of has the lock on the world supply of astaxanthin. Now, okay, so I said they make it by the tons. Geez, do people really ingest tons of astaxanthin? Well, actually, yeah, because why? Because this is added to the feed of salmon. The salmon that are pen raised, you have to add astaxanthin to their food to make the flesh pink or orange. This is the pigment that's present in salmon. The wild-caught salmon pick this up from their diet. They eat crustaceans that have this in their bodies because the crustaceans eat algae. The algae is the primary producer. But if you have big pens of salmon and you're feeding them dog food, then they don't, the flesh is going to be an unappetizing white, and so there's a market for astaxanthin. That's the big market. Thought you know that. Think about that next time you buy not wild salmon. Okay, now, so that's a little aside. Now, there's another problem with the Wittig reaction, and that is that it doesn't always give 100% Z product. Usually the product is Z. You get cis 1,2 disubstituted alkenes, but you don't get 100%, hardly ever. So in this case, this is a particularly bad case where you have phenols on both ends. You get about 60, about a 3-to-1 mix here. And, that's, okay, so you say, well, okay, 3-to-1 mix, what's so bad about that? I can separate them out. Yeah, but the separation of geometrical isomers of alkenes is a real bear. Okay, so that's not usually easy to do. So that's a problem with Wittig. So there are other ways to bias this reaction to get more of this or more of that, but we're not going to talk about that in 1973. Wittig shared the 1981 Nobel Prize with H.C. Brown. H.C. Brown is the hydroboration guy, and so those two guys were both rewarded with the Nobel Prize for their contribution. So that kind of gives you an idea of how widely used the Wittig is. Even with all the problems of having to recycle the phosphine oxide. We talked about this reaction. We talked about oxidation of aldehydes to carboxylic acids in Chem 272. Time to remind ourselves that yes, aldehydes can be oxidized. Now, what differs, what distinguishes rather an aldehyde from carboxylic acid? Just one red oxygen atom, right? And so this process can be done in a number of ways. Chromium plus 6 in the presence of water, as we discussed. Potassium permanganate can also do it in quite a good field, actually. And the reason is, and both of these reactions, by the way, are done in aqueous media. And the reason is, I indicated to you last time, the reason is because the oxidation takes place through a hydrate. And so in the presence of water, you have an equilibrium of the aldehyde and its hydrate. Now this hydrate looks very much like a secondary alcohol. And so if secondary alcohols are oxidized to carbonyl compounds, then here's a secondary alcohol. It's a very special secondary alcohol because it has already a hydroxy group. And so that's why you oxidize that and end up with a carboxylic acid. And so this is an easy oxidation to take place. Aldehydes undergo oxidation all by themselves, actually, in air. And so if you have an old bottle of any kind of aldehyde lying around the lab and you open it up, very often you'll see solid in there. Why is that? Well, because the carboxylic acids are very often have higher melting points than the aldehydes. And so they can be crystalline. So the aldehyde may be liquid, but the carboxylic acid is often a solid. Why would a carboxylic acid have a higher melting point than an aldehyde? What again? interesting reaction. You can also oxidize aldehydes with silver. And you can think of, silver, my goodness, that's expensive as a coinage metal. Why would you want to do it the expensive way? And of course, you're not going to do this on ton scale. But on small scale, it's sometimes a useful reaction because conditions are much milder than potassium permanganate or chromium +6. Strong oxidants which can oxidize other things in your molecule. Silver ion is a fairly mild oxidant and is not likely to interfere with any other functionality. And so on a small scale, this is sometimes quite useful to be able to do. Okay, so that kind of wraps up the chapter on aldehydes and ketones and carbonyl addition reactions. I'll start with a small review now and continue on Monday when we meet again. The exam will cover till the end of chapter 19, till the end of this chapter. Monday I'll have more to say about the exam for you. So this is an important chapter. So chapter 19 is really our introduction to the heart of organic chemistry, which is carbonyl chemistry. And these reactions are ones that have a great deal of importance, not just for organic synthesis, but also finding a counterpart in biochemical mechanisms. The key to the reactivity of carbonyls is the resonance structure that indicates to you that the CO bond is strongly polarized. And so the fact that you have a partial positive charge on that carbonyl carbon atom tells you that this is going to be reactive with nucleophiles. And it also indicates to you that there's going to be special reactivity associated with the alpha carbon atom. So, in other words, because this carbon, I'll show the charged resonance structure. Because this carbon atom has a partial positive charge, these hydrogens are much more acidic than you would have anticipated, right? So in the absence of a positive charge here, these are not going to be acidic at all. Because you have a positive charge here, these are acidic protons and can be lost. So once you lose one of those protons, you end up either with an enolate or an enol. And that tells you that the carbonyl group has actually kind of confers two kinds of reactivity on a molecule it exists in. So if I take, say, cyclohexanone, then it will react with nucleophiles at the carbonyl carbon, but it will react with electrophiles at this carbon. Okay, so you can form bonds nucleophile to the carbonyl, that would be a Grignard reaction, or you could form the enolate or the enamine, you'll see that, and allow that to react with electrophiles. And that is really at the heart of it. So it's a very simple concept. Applying it is not all that hard. We talked a bit about spectroscopy, and one of the things that we said was that the infrared was going to be particularly useful for us because the carbonyl group is the strongest group, the strongest signal in the IR, but also because you can tell an awful lot about the structure of the carbonyl compound just by looking at the frequency of the IR. So there's the sequence of cyclic ketones, which shows you that you can identify what cyclic ketone you have just by the IR spectrum with nothing else. We're going to see in later chapters that different kinds of carbonyls, carboxylic acids, esters, amides, have IR stretching frequencies that also are characteristic. For aldehydes, you even have the CH stretch, but as I indicated to you, it's much more useful to determine the presence of an aldehyde by the NMR, proton NMR. And then we talked about conjugated carbonyls, and we said that conjugation will weaken both the CO and the CC bond. That's indicated by a lessening of the stretching frequency of those two, and that is consistent with the resonance structure, which diminishes the double bond character at both CC and CO bonds. So that's as far as I want to get today. Question and answer is going to be tomorrow.